Hello everyone, welcome you all to the channel, and this video is going to be about Python. Let's start with Python and data structures and algorithms and a lot more things, right? Okay, so the objective for this video is very clear, it's to explain the importance of analysis of algorithms, their notations, their relationships, and solving as many problems as possible. So let us first focus on understanding the basic elements of algorithm, the importance of algorithm analysis, and then slowly move forward to other topics, right? And the main point is this video is, I believe at some points it's not going to be really very beginner friendly, but don't worry, as you proceed with the playlist you would get very acquainted with it and you'll really find it very simpler, very easier and everything, right? So without wasting our time, let's simply get started with the thing. Let's first talk about variables. So we are not directly jumping onto the Python right now, because I believe you might be knowing the basics of what do you call it, programming and all, right? But we will also be taking a look at everything, right? I want you to have a very basic understanding of Python. For it, I'll create a cheat sheet and you can go through it, once, and you'll get to know a lot of things about Python and all. I'll also try to have it done in the description box, right? So yeah, let's get started and let's continue with it. What are variables, right? So before going to the definitions of variables, you know what I want you is to relate them to the very old mathematical equation. All of us have solved many mathematical equations since childhood. For example, let's take an example: x square plus y square plus equal to, let's say, 2ab. I don't know, right? I think let's not have this 2ab. Let's change this 2ab thing to, let's say, 20, right? Let's say it's 20, right? Let's say 20, right? So we don't have to worry about the use of this equation right now, and the most important thing we need to understand is that the equation has names. Those are notably x and y, right, which hold certain values. Values means data, now that means the name x and y are placeholders for representing some sort of data. So similarly, in computer science programming, we need something for holding data, and variable is the way to do that. So data types is the second thing that we need to talk about. So in this equation, basically, right, the variables and x and y can take any value such as integral numbers, yes, right, integral values like 1, or it can take a value for you. Let's say x takes a value of 1 and y takes a value of 5, right? Second thing can be, it can be any real number, complex number, whatever, right? Real number can be like 0.1 or 0.5 basically, or it can be just 0, 1, or whatever be the case, right? To solve the equation, now we need to relate them to any kind of value they can take, and the data type is the name used in computer science programming for this. Now a data type is a program in a programming language, is basically a set of data with predefined values. Now examples of data types can be, you take integers, you take floating values, you take unit, you can take characters, etc. Now the point is, computer memory is all filled with zeros and one. If you have a problem and we want to code, it is very difficult for us to provide the solution in terms of zeros and ones. So to help users, programming languages and compilers provide us with data types. For example, you know float takes 4 bytes. This says that in memory we are trying to combine 4 bytes and calling it a float, right? That is 32 bits. So a data type reduces the coding effort at the top level, and there are two. So we have two types of data types. One is system predefined or system defined, right? Other is user defined, and these system defined are also called primitives. Cool. So data types that are defined by the system are called primitive data types, and these primitive data types provided by many programming languages can be int, we have float, we have double, we have characters, etc., etc., right? So the number of bits allocated for each primitive data type, it totally depends on what factors it depends. It is the programming language, it is a operating system, it depends on your compiler. Okay, and for the same primitive data type, different languages can use different sizes, and depending on the size of data types, total available value will also be changing, right? We'll take a look at it, right? So nothing to worry about. For example, let's say take 2 bytes, right? So what will be the range? That will be minus 2 raised to the power 15 to 2 raised to the power 15 minus 1, right? In that similar way. This is very basic things, that you might have studied during your school time as well. I remember I was in ICC, and there we had these all stuffs, the range of int, the range of float, and everything, right? So we're just, taking a gist out of it and trying to understand all those stuff. Then we have user defined type. So if system defined data types, I believe, are not enough to understand or to equate any value, then most programming languages allow users to define their own data types, and which we call as user defined data types. Good examples can be classes in Java, right? Classes contain all types of data types, right? Those can be integer, those can be functions, those can be each and every stuff, string, characters, and everything, right? You can just put all those in single class, right? And class becomes your user defined data type. Another point is data structures. So till now we discussed about data in variables. Now, okay, we have data. Now what? We want to do some manipulation. We need a mechanism, right? Right, we have to got the data, we need a mechanism, we need to do a manipulation. So we want a mechanism so that we can manipulate the data to solve a problem. And data structure is a particular way of storing and organizing data in a computer so that it can be used very efficiently. And a data structure is a special format for organizing and storing data. Now, general data structures types include, arrays, you can have list, you can have graphs, and many more things, right? But these data structures are of generally two types. Okay, let me just write those down. One is linear and other is non-linear. We'll get to all these both as well as later, but for a quick thing, elements in the linear can be accessed very sequentially, and when you can't access them sequentially, that's non-linear. Example for linear can be your linked lists, your stacks, your queues. For non-linear it can be trees and graphs. We'll come to it, right? Nothing to worry about. Okay, then we have abstract data types. I hope you might have also read about this. Those are abstract data types, right? So before we define abstract data types, let us consider the different view of system defined data types. See, we all know, that by default all primitives data type support basic operation such as addition, subtraction, multiplication, division kind of stuff, right? So the system provides the implementation for the primitive data type. For user defined data type, we also need to define the operations, right? So ADT basically consists of two parts, notably, right? One is going to be, we need to declare the data, declaration of data, right? The second thing is declaration of operations, right? So commonly used entities are linked list, stacks, queues, which are user defined basically. Dictionaries are some other examples, right? So while we define ADTs, we do not worry about implementation detail. They come into the picture only when we want to use them. So different kind of entities are suited to different kind of application, and some are very highly specialized to specific task, right? So by as we approach the tutorials, and or the playlist, we will be going through a lot of them, right? And we will be able to relate the data structures to the kind of problems they can really solve, right? So understanding the algorithms, right? So algorithm, you all know that it's a very simple thing, right? It's just like it's a step by step instructions to solve a certain kind of problems, right? Algorithms are step by step instructions that you can solve a problem. I don't really think we need to go really deep into this at this moment. It's really simple to understand. Let's say we want to cook something, right? We want to have to cook anything, like the chapati. What do we want? We need the pan. We need, let's say I want to make omelette or egg, right? I want a pan, I want oil, and then I want to break the egg. I'll just put it there, and in such a way I can just prepare the omelette. That's an algorithm, simple step-by-step instruction that was given to me, that I was performing, in order to cook my omelette or egg or whatever, right? So this is very simple, right? Now the important thing comes up, right? Why the analysis of algorithm? That is the real question that we are here for. Why analysis of algo? Why do we need it? So I want to go from city X to city Y, and there can be multiple ways, of accomplishing it. I can go by flight, I can go by bus, I can go by train, I can go by walking, bicycle, right? So depending on the availability and convenience, we choose the one that suits us, right? Similarly, in computer science, we have multiple algorithms available for solving the same problem. For example, sorting problem has many algorithms, like we have selection sort, we have quick sort, we have insertion sort. Algorithm analysis, basically it helps us determine which algorithm is the most efficient in terms of time and space being consumed, and this is the goal of analysis. So which is just like saying, we want to just compare algorithms mainly in terms of running time, but also in terms of other factors like how much memory they are taking, how much effort as a developer I'll be putting in it, right? So what is running time analysis? That is a second question that I should be answering. Okay, second question can be, one is this, number two is like, running time analysis. Okay, so it is the process of determining, right, how processing time increases as the size of problem or the input size will increase. Now input size is the number of elements in the input, simple, and depending on the problem type, the input may be different types. What can be the common types of input? Like they can be the size of an array, you can have number of elements in a matrix, you can have vertices and edges in the graph, right? And in a similar fashion there can be many more, like let me just write it down. It can be like notes for you as well, right? We can have size of an array, right? We can have elements in matrix, I've still not learned how to use this pen and all, right? Vertices and edges in graph, and many more, right? Many more can be there. So how do we compare those algorithms? Third question that might be, how how do we compare the algorithms? So to compare algorithms, we need to define certain objective measures. Number one is, we need some measurement things, right? One is how much time it takes to execute time, number one. Second is number of statements to be executed. Number three can be, what is an ideal solution? So not a good measure as an execution time are specific to very particular computer, right? See, these execution time can be like, let's say if I run a game, right? For example, if I'm running a game in, let's say a very high ended PC, right? And at the same time I'm running that particular game in a very old monitor or monitor set of computer, right? Definitely, I can't say that this particular application is really slow, because the problem was not with the application or the program or the code, it was a problem with the machine, right? So execution time, basically, it's not really very good measure, because it can depend on the computer. I hope you might have understood the point, that let's say I have a machine A and machine B. Machine B is more upgraded, right, version of A. So the same program will be slower in A as compared to B, but we got the comparison machines, not the particular code, right? So this is not really a good idea to do it, right? a number of statements to be executed. It's again not a very really good measure, because the number of statement varies with the programming languages and as well as the style of individual programmer. For example, I wrote the code in Python and you wrote the code in Java. Although the codes are doing same, right? I want to print hello world, right? Python will simply write a hello word in single line. Java will have it in 5 lines. It doesn't really mean that my code was more better than Java guy, right? It was simply the number of statements are less in Python, but it doesn't mean that his program is really slow. Are you getting the point? Number third is ideal solution, right? Let us assume that we express the running time of a given algorithm as a function of input size n, and compare these different functions corresponding to the runtime. This kind of comparison is exactly independent of machine time. This is independent of your programming style, independent of your programming language, right? And this is actually what we are looking forward to. So I want something that is the function of input, right? Are you getting the point? I need something that is a function of input size. Cool. So what this leads me to the question of rate of growth. See, when my function is working according to the input size, there is a rate of growth, right, coming up. So now I'll talk about rate of growth, how much the things are growing up, at what rate are those growing up, right? As you might have witnessed about differential calculus and all, right? There we talk about rate of growth and everything. So the rate at which the running time increases as a function of input is basically the rate of growth. Now let us assume that you went to a shop and you went to buy a bike and a cycle, right? So if your friend sees you there and asks what are you buying, then in general you will be saying I'm gonna be buying a bike. This is because cost of the bike is high compared to the cost of cycle. No, approximately the cost of cycle is to the cost of car, right? So approximating that way, you know. So for this example, now we can represent the cost of car and the cost of cycle in terms of function. And for the given function, if we ignore the low order terms and that are relatively very insignificant, right, for larger values of input size n. This is an example. Let's take an example like what really matters to us. For example, you I have something as let's say n to the power 4 plus n to the power 2 plus 100 plus 1 plus 0.5 equal to something x, right? Cool. So whatever answer I would be getting out of it, it would somehow be more or less influenced by this. It will have a better influence on this thing, right? This is gonna have more influence rather than the 0.5. So even if I would not consider the 0.5, it won't, I don't really think so it would make a lot of sense to me, to the solution. Even if I would remove this one, even if I go with the 100, or let's say the value of n is, let's say 1000, when I compare this 1 2 3 4, I would see the influence of this would be really relatively very high, right? If I had to go, this n4 would be like n to the power 4, and then n to the power like somehow this a and 100 is, and those are going to be really those won't really matter. So this is what we are talking about, growth of rates, which actually influence uh, the the solution more, right? That is what we are trying to look forward for. Okay, now types of analysis, but now we know that there is something called growth of rate, rate of growth, and we also know that what can be the ideal solution for something, right? So the next point makes that really important, that is what all types of analysis I can do with this, what type of analysis I can go through it. So you can basically go into three. So when you are analyzing an algorithm, we need to know which input the algorithm takes place and with which inputs the algorithm takes a long time. So we already have seen that algorithm can be represented in form of expression. That means we represent the algorithm with multiple expression. One for the case where it takes less time and another for the case where it takes more time. Now in general, the first case is called the best case, second case is called the worst case for the algorithm. To analyze an algorithm, we need some kind of syntax, and that forms the base for asymptotic analysis notation. So there can be three. Number one is worst case, second can be the best case, third can be the average case, right? See, the average case, let's talk about it first, right? It provides a very prediction about the running time, it provides a prediction kind of thing, and it assumes the input is really random, Second will be the best case. It defines the input for which algorithms takes the least time, right? And input is one for which the algorithm runs the fastest. But this worst case, it defines the input for which algorithms takes the longest time, right? And for which the algorithms become really slow. This is what we are really looking for. Okay, this is only up to this. I'll add a page. Okay, I have added a new page to it. Let's do it, right? So what this really mean is I have something that is lower bound, okay, which will be less than average time take with upper bound. If I have to make a graph for these, first case, best case and average case, I'll have three kind of conditions coming up, right? So for a given algorithm, we can represent the best, worst and average in forms of expression. Now as an example, for example, let's take there are two algorithms, right? Fn equal to n square and Fn is equal to n plus 100 n plus 10n, right? So which of these two do you think is going to perform well? I believe this one is going to perform well, more better in that's simply 11n, but let's say why? Because it's in a square form, it's increasing with the number of inputs that you have, right? So this is going to be the worst case. This can we can consider it the best case, let's say, right? So similarly, you can take any sort of example for average. But now the question comes is, I just told that we use asymptotic notations, right? What actually are those? So ASYMP asymptotic notation. Yeah, I you might have heard these about, in the class 12 there was a chapter about, I guess, curves, why we were having parabola, we were having hyperbola kind of stuff, right? That was the first time you might have heard about this particular thing, asymptotic notation. Now having the expression for the best, average and the worst case, for all the three cases we need to identify the upper and the lower bounds. Now to represent these upper and lower bounds, we need some kind of syntax, and that is the subject for the discussion, right? So let us assume that the given algorithm is represented in form of a function n fn, right? We'll take that into the consideration, and first we'll talk about where's this gone? Okay, we have it in a function fn, right? So let's talk about big O notation. Yes, it will definitely help you out, right? So this notation gives us the tight upper bound for a given function. What do we mean? We will just get. So let me first just draw the graph for it. It would certainly look like, let's say there we have a CGN function going on. Let me just go with the green, right? Then we have a graph for the function, right? So let me there we go, right? This is our function fn. Then let's call it CGN, CGN. Okay, let's understand this first. So what actually means is, it is represented in this particular form, whereby function fn is equivalent, it can be called equivalent to CGN, right? This means that the larger values of n, the upper bound of fn is gn. For example, if let's say we have fn equal to, let's say we have fn equal to, let's call it n4 n to the power 4, then we have 10n square or something like that. So then n4, this upper bound is going to be cgn n to the power 4. This is what this means actually. So that means gn gives the maximum rate of growth. So gn here gives you the maximum rate of growth for fn at a larger values of n, as the values increases. So let us see O notion with a little more detail. O notion, defined as, so technically what it says is O gn can be defined as fn, right? So there exists a positive constant c and n naught, such that n naught will be this value, right? Here we will have, let's say, n naught as a value over here. So there exists a positive constant c and also a n naught, such that fn is going to be less than, is going to be greater than 0, but it's always going to be less than cgn for all values of n which are greater than equal to n naught, right? This is what we get the equation for big O notation, and gn over here is actually the asymptotic tight upper bound. As you can see, gn is always above the fn, right, which is greater than equal to the given algorithm rate of growth, exactly, right? This is what we call as big O. So generally we discard lower values of n. That means the rate of growth of at lower values of n is not at all important for us, right? So in that figure, so I wanted to do some sort of visualization thing with it, but let's first do some sort of questions, right? Let's see 2-3 questions coming around these. Just red pen for that. It is a certain questions coming up around for these. Where has it gone? It's such a problem. Okay, let's say I want to find the upper bound for let's say there is a function fn which is equivalent to 3n plus 8. These questions generally come in the university level exams, but yeah, let's try to solve these as well. These might help you out later. Okay, figuring it out. So I can say 3n plus 8 is gonna be less than what's gonna be the next bigger value. Let's call it 4n, right? In such a way, if I would solve this, if 3n goes this way, that is 4n minus 3n, it will be like 8. So n will be greater than or equivalent to 8. So for this particular value, if I would take 3n plus 8 is certainly going to be equivalent to n. N is going to be the upper bound here, right? With whatever is the value of c, I can take the value for c as 4. This particular thing, cgn basically you need, cgn is the value that you need, and c is going to be 4 and n naught, what would be 8, this particular value, right? So this is how you solve such kind of questions. These come at university exams. Maybe these can help you later as well, but yeah, still. So let's do another question. Find the upper bound for, let's say, fn equal to 2n cube minus 2n square as well. Like, let's do for this as well. I would say pause the video, try to solve it yourself, and now let's see how to do it. Okay, for this particular thing, I'll simply write 2n cube minus 2n square. It will simply be less than 2n cube, I would say, right? Because this won't have really a lot of influence on it, right? For n will be greater than, whenever n will be greater than 1, because see, these both will cancel and this will come here, only one will be left over here. So whatever you want to do, right? Not really a big problem, right? So we will have 2n cube minus 2n square will be equivalent to O of 2n cube. But with this n cube, will exactly 2 matter? 2 matters? No, not at all. So we will have c equivalent to 2, that is c gn, right? And n naught is going to be equivalent to 1, right? Simple as that. Okay, let's say So there is no unique set of values for n naught and c in proving the asymptotic bounds. Let us consider, see, which means that there can be multiple solutions for the same question. Let's say, okay, I'll explain to you this particular thing as well. Let's say in case 1, let's say, we have something called as 100n plus, let's say, 4 is equivalent to on, right? So there can be two solutions for it as well, right? See, one can be that 100n plus 4 is less than equal to 100n plus n. I'll just added a very small value n and took it a bit above this particular thing, right? So which means 101 n can be less than 101 n, right? So for any value where n will be greater than equal to 5 and n not equal to 5 and c equal to 101, this is what this particular thing means. This is one solution that I'm getting for it, right? But at the same time, there can be another solution for it, that is 100n plus 4 is less than 100n plus 4n, right? This can be a solution for it, which is equivalent to 105n 104n is less than equal to 104n, right? For any value of n not going to be equal to 0 and c is going to be 104, so sorry, I made a very small mistake over there. It was 101, right? I was just writing down it really quick, so 101. But did you see, there's no uniqueness to the solutions that you get, so either you could have this answer, one could get this answer, one could get this answer. Same goes for these all answers as well. Someone can have some different answers for these, and it totally depends on you and and the approach you took, right? There is no correct answer, and there is none of them was correct. I would say both of them were correct and both of them were not incorrect as well, right? Okay, the second thing is omega notation. See, although big O is the notation that we really care about, but let's, just for the sake of discussion and all, let's take this as well. How does the graph would be looking like? So similarly, like O, this notation gives us a tighter bound, but which one? We'll take a lower bound in this case, right? We generally take that. So let's say if I have a function going like this, right? This is my main function. Then in this particular case, what I will be taking is lower bound, c, g, n. This is the lower bound that I'm going to take, right? So this means at larger values of n, the lower bound is gn, right? For example, you see, the answers that you get here and there, they can be almost similar, right? So there's nothing to be worrying about. These are all literally the same, right? And nothing to be really afraid of, right? For example, in this particular case also, let's do a question and you'll get a very better understanding of it, right? For example, if I find the lower bound, but this time find lower bound for fn equal to 5n square, right? So for all c, for any value of c, before that, such that we have 0 less than cn square less than equal to 5n square. Okay, but first, before I solve this problem, let me just also mention you some sort of things. I don't really want you to get confused with it, but let's discuss that particular point as well, right? So we just need a lower bound, right? So the omega notation can be defined as like, we have omega, and this is how we generally write it. I just thought I should give you an understanding about this as well. Will be equal to fn. So there exists a positive constraint c, and again you will have something called n naught, but it will be something like 0 less than equivalent to cgn less than fn, right? For all n should be greater than equal to n naught. Not, let's take something n naught here, right? And what did we had the condition over here? It was something like this: 0 less than fn less than cgn, but this time the condition became 0 less than cgn and less than fn. And this can totally be seen from the graph as well. It's really simple. If you take a bit of time, you take your pen and paper, take the notes and everything, you'll definitely figure it out that it's not really that tough. Okay, let's continue with the question. Okay, the page size is this much. I was like trying to figure out like why it's not rolling up or something. Okay, so 0 less than cn square less than 5n square, right? So which equates equivalent to cn square is less than 5n square, right? And that gives me a solution that is equivalent to c will be 1 and n naught is equivalent to 1, which means 5n square is giving me a value that omega will be n square and c will be 1 and naught will be 1. Really simple one, right? Let me just erase all this and take a look at the final one, right? That is theta notation. Okay, so for the theta notation, let's again have a graph coming up with it. And so for the theta notation, it decides whether the upper or lower bound of the region are same or not. Now the average running type of an algorithm is always between the lower bound and the upper bound. Now if the upper bound O and the lower bound omega give the same result, then theta notation will also have the same rate of growth, right? So how does this look? I'll have a function going on like this, fn, right? But no, I'll have something be going like this, that is this, and let me take this way, right? So c2 gn and c1 gn, right? Lower bounds and the upper bounds, right? So for example, if there is something like 110n plus n, so its tight upper bound will be on, and rate of growth will at the best case will also be on. Simple as that, right? Okay, you'll get a better understanding of. Okay, first let's write the notation how actually it looks like. Okay, that's the most important part, is the mathematical one, right? So we have this theta n is really so sorry, theta gn, right? Theta gn, let's say taking, it's gonna be fn, but when, so there will be two constraints now, c1 and c2, because we have to take the value which is in middle of both, right? And also n naught, right? Such that 0 will be less than c1 gn less than fn. Fn is going to be sandwiched between c1 and c2 for any value that you take that is greater than equivalent to n naught, right? This is the simplest mathematical formula that you would get. And gn now is an asymptotic tight bound between, for fn, and theta gn is the set of function with the same order of growth as gn. Okay, so if let's take a question as well for this. Let's say we have the question, let's say, like for example, let's say you thought about theta bound for let's say a random function like n square by n minus n by 2, right? If you take this into the consideration, how would you solve it? I believe you might have written this down. Just write this down particular thing, and because we will be solving using this particular equation, right? So I have this n square by n minus n by 2. Now I need two values over here. This can be greater than n square by, let's say, 5. This can obviously be greater than. These are all arbitrary values, by the way, right? For all value of n greater than 1. So whenever I'll take any value greater than 1 of n, let's say I take the value 2. Let's say I took the value of 5. 5 by 25 by 5, it's going to be 5. 5 and 5 by 5, that is going to be 25 minus whatever be the case, and this as well, right? So whatever be the case, I guess these values are going to be really correct. So by 2 minus n by 2 will give me a theta of n square, right? That is, and what's the value of c1 now? C1 will be 1 by 5, right? What's the value of c2? C2 is going to be 1. What's the value of n naught? That's going to be 1. This one, right? Isn't it really simple? uh, Whatever you take, right? For why is it called asymptotic notation, right? Why do we call it as asymptotic analysis? See, from the discussions that we have dealt in now, for all the three notations, whether you talk about the best case, you talk about the worst case, you talk about the average case, we can easily understand that in every case for all given functions, we are trying to find another function gn which approximates fn at a very higher value of n. So that means gn is also a curve which approximates fn at a very higher value of n. So in mathematics, we all call such a curves as asymptotic curves. In other terms, gn is the asymptotic curve for fn. For this reason, basically, we call algorithm analysis asymptotic analysis, right? There are certain guidelines, when you talk about asymptotic analysis. It's really a lot of time-taking things. Like when you talk about loop, right? So we take certain constants. When you talk about nested loop, we need inside out, right? So total running time is the product of size of all loops, right? When you talk about consecutive statements, we add the time complexities. If we have if then else condition, we take the worst running time, because there's a test plus either the part or else part, whichever is the target, right? Whatever is the kind, if you talk about logarithmic complexities, it's similar, like because the algorithm, if it takes constant time to cut the process by friction, so right, we'll see certain examples, but for this video I believe this is something that it should be, and we'll have more of such videos coming up. In the next videos we will try to make things more simpler. I guess you might have got a very high level understanding of what actually all those things are, right? But we will equate all these videos, all these stuffs, and make them really simpler in the coming videos, right? And we'll try to solve more questions. We'll In the next video we will talk about divide and conquer, we will talk about master theorem, and we'll talk about guessing, we'll talk about confirming, and there's a lot more things to be discussed, right? Problems and solutions of some algorithmic analysis. So this is going to be really helpful with your college perspective as well, and with your other DSS stuff as well for competitive coding and anything, right? So this will really help you out. Thanks a lot for watching the video, and I'll see you in the next video. Till then, practice these things, try to understand all of these. Comment down whatever you want to learn next and everything, see you.